Okay, so today we will work on two different subjects. One of them is the application of the motion of the charged particle under the magnetic and electric field. Basically, you know that the motion of the charged particle, if there's a uniform magnetic field, so what will happen? It will gyrate. So basically, the equation of motion is the change of the momentum with time, E over C, V cross B. And the particle can move with relativistic momentum. But if it is in the uniform magnetic field, the speed will be a constant, and you can write the rate of change of the velocity in time as a V cross omega B. Omega B is the gyration frequency. So where this is E B over gamma MC. So in the Lorentz factor, the magnitude of speed is constant, therefore the Lorentz factor is constant, but the velocity is changed because the particle is gyrating under the uniform magnetic field. And so you can write this in relativistically. So you know these things. So what happened if you let move the charged particle under the electric field and magnetic field? So suppose that there's a uniform electric field in Z direction, and suppose that there's a uniform magnetic field along X direction, and so this is the one spatial case of the distribution of the fields. So suppose that they are uniform. So you know that what you have to do, you have to write that the Lorentz force and to solve the equation of motion. So if there's a E and B, this is a complicated differential equation. You can solve, but using the Lorentz transformation and the field transformation, sometimes you can solve such a problem much more easily. So suppose that you have some frame, and this frame moves with velocity as E cross B. So suppose that the frame is moving with that velocity E cross B. E cross B is along the, so if we call this is the X, Y, Z, so E cross B along the Y axis. So what kind of fields we have in that frame? Suppose that the magnitude of the electric field is less than the magnitude of the magnetic field. You can do the opposite of them. So basically, the fields or the Lorentz force in the new frame, let's say new frame is moving to the right, let's say in the K prime frame, that is nothing but dP over dt prime, and charge is the same everywhere, E prime plus V prime D prime over C. So in the new frame, so let us look at the fields in this moving frame. So basically, we work on the field transformations last time or last week. E prime was gamma E U cross B over C, and we have minus gamma square over gamma plus 1 U over C dot E, and for B prime we have gamma B U over C cross E minus gamma square gamma plus 1 U over C dot B. So if we are moving with this frame, basically you will see the several things are 0 there. So if U is E cross B, then automatically you see that the U cross B dot E is equal to 0. Okay, in that frame this will be 0, and similarly what else? U dot B will be the 0 because they are U cross B. Okay, and how about the electric field seen in this moving frame? So you have this term, and if you take the U and plug it there, you will obtain what? E prime will be gamma E plus what? 1 over C, and C E cross B over B square cross B. So I think I take it correctly. Yes, C's will be cancelled. And what is this? So what is this? This is equal to the following. So gamma E. So you have take this as a minus sign and use that the double cross product rule. So you will have B square along E and E dot B. So basically this situation will be the following: minus B square along E, and this should be divided to the B square, and the other term B dot E over B square. So let us look at whether I did correctly or not. So take this to the other side as minus, and then so use this A cross B cross C. So take this at the other side as a minus sign, then A dot C will be the B square along E, and the other term E dot B. Okay, so E dot B is 0, and then so B square magnitudes are cancelled out, and you can obtain that the E prime is 0. So in this new frame, E prime is 0, no electric field. And what about the magnetic field? So do the same thing for the magnetic field. So let me write there the E prime is 0 and study for the magnetic field. So E prime is 0 in the moving frame with velocity as a E cross B. So if you look at what is going on for the B, you will obtain the following. So do the same thing for the B prime gamma B, and 1 over C. Again, U cross E is C E cross B over B square cross product with E, and so in that case the situation is the following. So if you do the same thing, you will obtain gamma B. C's are cancelled, so minus E square B over B square, and minus or plus, it doesn't matter, E dot B over B square along E. So let us look at this. So take this to the other side as a negative, this will be positive. Then A dot B, that is 0, minus E dot E is E square and this term. So E dot B is again 0, and what is left? Leftover term is in the gamma parenthesis and gamma B parenthesis 1 minus E square over B square along B. And what is the E square over B square? E square over B square, from here you can see that what is, if you take the magnitude of this, that is E over B is mu over C. So from here E magnitude over B magnitude is U over C. And basically this is 1 minus beta square, and 1 minus beta square is 1 over gamma square. So this term is 1 minus beta square, or 1 over gamma square, and that is beta over B over gamma. So in this new frame, it is what is seen, the magnetic field only seen is reduced by a gamma factor. And basically, you don't have to solve the equation of motion for the Lorentz force. Now, for this, if you have a uniform E and B field, the situation is the following. So if the frame is moving as a U cross B, it is called as a U cross B drift. You will see that the magnetic field only, no electric field, and the magnetic field, you know that how the charge particle moves in the if there is a uniform magnetic field. So dp over dt, that will be dp prime over dt prime, E over c, b prime cross b prime. So basically, in the new frame, so it will, the charge particle will try to gyrate, but at the same time it will drift. Okay, so B is outside, so the charge particle will try to gyrate, but it will drift. Okay, so I think this is the positive charge particle, the other one is the negative. You can work on this. Okay, so this is called the E cross B drift, and this is a very simple application of the Lorentz force. What you know that the motion of the charge particle under the uniform magnetic field. What we have done, we try to find a coordinate such that electric field goes to 0, and only left over is the magnetic field. And you know that what the charge particle does if there is only magnetic field, uniform magnetic field. So as you see that this was the case of B is greater than E. So if you do the same algebra for the opposite case, so you did it by yourself, you do it by yourself, the situation will be the following. So basically, in that case, the bottom line the following. So dp prime over dt prime, E and C is the same in all frames, and E V prime cross B prime, and you know that how the particle goes on if there's a uniform electric field and magnetic field. So quickly let us investigate what will happen if E is greater than B. So I will not do the step by step, but I will just write the result. So if you have this case, this is also interesting. What you are going to find the following. If E is greater than B, and if you use this frame, and at that frame you will see that the whole magnetic field is 0. And what else? The whole electric field will be, in that case, this should be related with the, I think that whole electric field in that case will be E over, I think, gamma. So do it by yourself and confirm. So that means that if the electric field is greater than B as a magnitude, what is the motion of the charged particle in that case? There is no magnetic field, only electric field. What do you expect as a motion? Q times E divided by mass is the acceleration. The force is QE in that case. And in that case, you will see that the charged particle is making what? A parabolic motion if it is positively charged. Because the force will be along the QE. QE will be the force on the charged particle, therefore it will drift along the magnetic field. So it will drift, but at the same time it will do a parabolic motion along the magnetic field. So this is a very nice and simple application of the field transformation. So you can solve the differential equations and so on, find this result, but in that way you can find much more easily what you are going to do. Now, let us back to the major stuff. So major stuff is now we work on last time the Lagrangian for the relativistic charged particle. We write in the covariant form, then we take the interaction with the electromagnetic field and we write the Lagrangian for that. So basically we studied that the Lagrangian and equation of motion of the charged particle under the electric and magnetic field. Now we will jump to different subject. Different subject is the motion of the electromagnetic field itself, not the charged particle. So as a tool, we can use the same principles of the equation of motion, but instead of the coordinates in the Lagrangian, the coordinates are what? Position and velocities. But now the coordinates will be the fields and the derivatives. Okay, so basically you have a Lagrangian for each charged particle or mass or whatever has the coordinates qi and qi dot. We can call this position and the velocity also, okay? So if you have several particles or some that in the system, you have to sum up those things. But if we can write the Lagrangian and find the equation of motion. But if we have fields, in that case the situation different. So what is changed? Qi goes to field and Qi dot goes to derivative of the field. And you can have more than one field, okay? So then you can add a k. K represents here, you can have at the same location of the space and time, because this is 4-dimensional. This is also 4-dimensional. X's are 4-dimensional. At any point in the space-time, you can have more than one fields, okay? Not necessarily one. This is just for the presentation. Sorry, representation. Then we will apply this for the electromagnetic fields. So then the definition of the Lagrangian is the Lagrangian density denoted by this notation. The coordinates are the fields that could be more than one at any time, and the derivative of the fields. Derivative of the fields. K could be more than one, okay? And since this is the Lagrangian density, it is defined as the Lagrangian is defined as a volume integral of this. So L is the Lagrangian density. Volume integral is the Lagrangian. So this is the basic change. Then how we define the action? What was the action here? Action was L dt. dt wasn't constant, not a constant, dt was changing in frame to frame. Then we write this in terms of proper time as a gamma d tau, and we define the Lagrangian in that case. Then the action here is the following. So you can guess what will be the action. If this is the whole Lagrangian, you have to integrate by time. So basically the action is Lagrangian density integrated through the volume and time. Then we can call the d cube x dt as a four-dimensional integral. And I show you that one thing, this four-dimensional integral element is the same in all Lorentz frames, inertial frames. So basically d to the 4x, d to the 4x prime are the same. So this is the action. Volume element of the action is four-dimensional, space and time. This is invariant in any Lorentz frame. And in order to get the equation of motion in covariant all the inertial frames, this Lagrangian density should be invariant quantity. Okay, invariant. So it shouldn't change from the one inertial frame to the other inertial frame. Basically, we will set up the Lagrangian density using the what? Scalars. And so this is the action integral. And what is the equation of motion? So we said that if you have from the classical mechanics, you know that if you take the variation of the action equated to 0, then you will find the equation of motion, d over dt del L over del qi dot minus del L over del qi. Okay, this is the equation of motion. And if you do the same thing here, what is the equation of motion? So basically, this is four-dimensional, and you will have, instead of d over dt, you will have del beta, beta is 0, 1, 2, 3, of del Lagrangian density over del beta phi k. So Lagrangian density is depending on the derivatives of the fields. So this is the derivative of the Lagrangian density with respect to the derivative of the fields, like a velocities, okay? Minus del Lagrangian density over del the coordinates, fields, okay? So del phi k have to be equal to 0. So this is the Euler Lagrange equation. If you have fields, and so Lagrangian density could be expressed the fields and the derivatives. Fields like coordinates, derivatives like acting as what? Velocities. So what you are going to do, you are taking the Lagrangian density, take the derivative with respect to the derivative of the fields, and then x the derivative. So derivative here is not depending on the time, it is also depending on what? All time and space. So beta and beta have to be summed. So it's a dummy in this here. So you have to sum this for 0, 1, 2, 3. And this is the other part of the earlier Lagrange equation. So Lagrangian density, derivative of the Lagrangian density with respect to the coordinates. So these are the definitions. Okay. So coordinates replaced by fields, derivatives of the coordinates, so this is the derivative of the coordinates replaced by the derivative of the fields. So Lagrangian is replaced by Lagrangian density, and the Lagrangian is defined under the volume integral of the d cube in x integral of the Lagrangian density. Action by definition is the same. So Lagrangian, this piece is for the Lagrangian L, and the other integral for the action, and that makes a four-dimensional integral of the Lagrangian density. And if you take the variation, if you find that the equation of motion, you will find that the equation of motion of what? Not a charged particle. You will find that the equation of the equation of motion of fields. Okay. Now let us. This is the general definition. Let us try to apply this general definition to the electromagnetic fields. So basically, the situation is the following. Instead of fields, we have which fields? We have four potentials. Four potentials are the fields. And we know that the derivatives of the four potential of the fields. So you can write that the equation of motion for the electromagnetic field, taking the fields as a four potential and the derivatives of the four potential, you can write in the following format. So del beta over del Lagrangian density over del beta A alpha minus del Lagrangian density del A alpha. So if you look at the left and right, there is one difference basically seen. What is that difference? How many equations here? This is dummy contracted. One equation here. Okay? You have to write 0, 0, 1, 1, 2, 2, and 3, 3. Okay? But if you look at here, how many equations you have? What is the free index? What is the free index? Alpha. So basically alpha is 0, 1, 3. You have four equations. Okay? So this is the format of the earlier Lagrange equations. So what is next? We have to find a Lagrangian density. So what we are going to find? We are going to find what? Maxwell's equations. So what is the Lagrangian density? So at this point, we will set up again the Lagrangian density from the scalars. Maybe you did, I give you homework last week. that was the homework. Find the f tilde alpha beta, f alpha beta, and find the f alpha beta, f alpha beta. So did you do this example? So basically you obtain scalars in both cases. So one of them was minus 4 E dot B, and the other is minus 2 E square minus B square. Okay? So these are these quadratic? Yes, these are multiplied to each other. What are these are made of what? From the derivatives of the fields. Okay? F is f alpha beta del alpha a beta del beta a alpha. So can we choose one of them or both of them? So they are scalars. We can choose both of them, but one of them is unlikely because of the nature of the scalar. So in chapter 6 we haven't discussed, but you can look at that, and also you can look at the Landau-Lifshitz. There are two types of vectors, not a vectors, yes, vectors. One is the polar, the other the axial. So the difference is the following. If you have a vector, if you take the spatial inverse or parity, what do you know that the parity? Instead of xyz, you will just put minus xyz. So polar vectors are defined as in following. So let us give any vector k, for example. When k of x, when x goes to minus x, polar vector is what? Negative of this. Okay, so it changes direction improperly. Okay. The other type of the vectors is the axial vector. And in that case, when k of minus x, when x goes to minus x, x is equal to xyz, this doesn't change. So the nature of this one is the mixture of this. It is called a pseudo-scalar. So basically the situation is the following. Let me give you an axial vector. Think about the A cross B. A cross B. A cross B is this. When A goes to minus A, when B goes to minus A, is the A cross B change? No, axis is the same. Okay. So this has the same character. So basically, B behaves as a magnetic field, behaves as a axial vector. Electric field behaves as a polar vector. The scalar product is called a pseudo-scalar. Means that under the parity inversion or improper Lorentz transformation, it changes sign. Okay. So basically, I am going to eliminate this one for the choice of the Lagrangian density. Okay. So we don't have this problem here. So one thing I have to tell you this this is a pseudoscalar, but if you take the square of this, this is not a pseudoscalar, that's scalar. Because E goes to minus E, B is the B, but altogether pseudoscalar, that means that it altogether change its sign under the parity inversion. But if you take the square of this, this is a scalar again. So for more, you can look at the Landau or Lifshitz also. So, but the square of this is more complicated because the degree of this what? E square, B square of E, B, and square is the fourth order. So it is not likely for the Euler Lagrange equations. So this is the second degree of equations. So basically, as a scalar quantity, I will take the, although everybody agrees as a Lagrangian density have to be F alpha beta, okay? So one piece will be that. Now so is it affected by the gauges? Is it gauge invariant? Yes, it is gauge invariant because the elements of this electric field and magnetic fields. The electric fields and magnetic field doesn't affect it from the gauge changes. Okay, we have seen in the chapter 6 under the gauge transformations, electric and magnetic field doesn't affect it. So what scalar I can choose? So you know that the other scalar that was similar to the U dot A. Now the other scalar could be J alpha, A alpha. Okay, so that is the interaction of the for potential with the current density. Okay, that could be the other scalar. This other scalar, so let me write the Lagrangian density. Okay, then let us try to find the equation of motion. So basically, the Lagrangian density could be written is minus 1 over 16 pi F alpha beta minus 1 over C J alpha A alpha. Then I will try to find the equation of motion. But one thing I have to tell you, for the gauge invariance, I told you that this is gauge invariant, but this is not gauge invariant. Lagrangian density will change if I introduce a gauges. So what is the gauges? So you can say A alpha goes to A alpha, del alpha of something like this. Okay, so first term is del over del t, other is the gradient. So then you have to look at the action integral. The important thing is the action rather than the Lagrangian density, because using the variation of the action you are deriving the Euler Lagrange equations. If you look at the action integral for this piece, little piece, so this is just to give you information. So action integral, so if you look at the action integral, all pieces, and if you take that all of the Lagrangian density, so that will be what? 1 over 16 pi F alpha beta minus 1 over C. This is the action integral. What else I have? J alpha, A alpha, del alpha, d to the 4x. So let me concentrate this piece. So this is the part of the Lagrangian. Extra term is this. Okay, so let us look at that term. So that term is equal to what? J alpha del alpha, the gauges we introduce. So you can do this component by component, or you can write in general. If you perform an integration by parts, what will happen if you call this is a total differential and this is some other term of the for the integration by parts? This turns to be what? A minus del alpha J alpha times the gauge integrated through the volume. So this piece is the integration by parts. So you can do this by yourself. Component by component. So I am not going into too much detail. So basically you can change the derivative, and you know that what is the del alpha J alpha? What is this? J alpha del alpha J alpha. This is the continuity equation, continuity of the charge density, and that is 0. Okay, so this term is 0 because this is the continuity equation. So basically the bottom line is the following: if you introduce a gauge transformation, Lagrangian density change, but the action doesn't change. If the action doesn't change, equation of motions will not be affected. Okay? Now we are ready to work on the earlier Lagrange equations. So we set a Lagrangian density. The Lagrangian density made of scalars under the action that is gauge invariant. And let us try to evaluate the elements of the earlier Lagrange equation. So let me write again the earlier Lagrange equations. Del beta, del Lagrangian density over del of velocities, let's say, changes of the rate changes of the fields in 4-dimensional, like velocities, derivatives of the fields, okay, minus del Lagrangian density over fields. So we have to evaluate this. Operation. So let us start the study writing this f alpha beta in terms of del beta a alpha and so on. So we can write that the f alpha beta is by the derivatives of the 4 potentials. So let me write the Lagrangian here in the following formats: 1 over 16 pi, and instead of alpha beta, let me write f mu nu. Maybe this piece is okay. Del not a f mu nu, lambda mu. So let me write as a lambda mu. Del lambda a mu minus del mu a lambda. So this is f lambda mu. So which is corresponding to alpha beta. If this is lambda mu, this term should be f lambda mu in the downstairs with the downstairs indices. But I can write this whole stuff in the following form. Del mu a sigma minus del sigma a mu, and here use the metric tensor lambda mu g mu sigma. So let us look at this piece, what we have done. If you contract the mu and mu, what happens? This is the metric tensor. What happens? This goes to what? If you contract mu and mu, what is the free index? Lambda. So what happens? Del lambda. If you contract the sigma and sigma, what happens? A mu. Okay? And if you go to do the same thing to the other one, you will obtain that the del mu a lambda. And what is this altogether? F lambda mu. Okay? F lambda mu is F alpha beta, they are the same. So say, change this, they are dummy. So say that lambda mu and lambda mu. Okay? So I take the all indices to upstairs because I am going to take the derivative with respect to the upstairs indices. Okay? So I do this using the metric tensor. Now, let us look at the other term. The other term is there. That is nothing but minus 1 over c j alpha a alpha, or any indices you can use. So we are coming to the important stuff. So we have to take we write that the Lagrangian density with upstairs indices, then we have to take the derivative with respect to the del beta a alpha. Del Lagrangian density over del beta a alpha. So what will be this? We have minus 1 over 16 pi. So I write this coefficient because it will help at the end. And g lambda mu g mu sigma, and let us play on with the derivatives. So I am going to take the derivative of this with respect to that. If beta and mu is not equal to each other, that will be 0. If alpha and sigma is not equal to each other, that will be 0. We can express this using the chronicle delta. So the representation is the following. Chronicle delta mu beta, and for the other one, chronicle delta. So tell me the other representation. So if mu and beta is not equal to 0, that is 0. If they are equal, that is 1. I express this as a chronicle delta as mu beta. So what will be the other one? This piece. What is the other piece? Sigma and alpha. If sigma and alpha are different, that will be 0, otherwise 1. So then you can write the other piece as a sigma and alpha. So everybody agrees this? And this is the derivative with respect to this. What is the leftover? Multiplied that term, and that term is f lambda mu, f lambda mu. Okay, so I will do this by step for the other terms also. So do you agree this? So in order to speed up, you can also tell me what is going on here. So what will be this one? So say quickly. This will be chronicle delta sigma beta, chronicle delta mu alpha, multiplied with this term. So the other term will be minus chronicle delta sigma beta f lambda mu. So let me control, this is the important point, so we have to control again. Sigma beta mu lambda multiplied with f lambda mu. So now let us switch the other derivative here. Okay. So what are the other derivatives? Take the derivative with respect to this. That will be lambda beta mu alpha multiplied with the other term, that will be plus chronicle delta lambda beta chronicle delta mu alpha. So is it okay? Lambda beta mu alpha multiplied this term, and what is that term? What is that term? What is this? Mu sigma. Mu sigma, thank you. Mu sigma. Mu sigma. So I have one more term. Chronicle delta mu beta lambda alpha. So with minus sign. So I will calculate this equation of motion and we can go for today. So I am not going to give a break. 10 or 15 minutes we will work on. Then that's all for today. This is a long expression, especially in my handwriting. So it is mu beta lambda alpha and multiplied that term. Okay. So by the way, what is the degree of this Lagrangian density? It's quadratic, because this multiplied that, this multiplied that. Okay, this is in the quadratic order. And the earlier Lagrange equations will be that form. So now let us try to investigate what we have found. So we have to make some work here. So let us think about that the contraction of mu and this mu. What will be the leftover term? If you contract the mu and mu, what will happen to G? What will be the free index? If you contract mu and mu, this will be what? Tell me what will be the G? G lambda beta. Beta is the free index. And do the same thing to here. Sigma and sigma. Contract this. What will be the G? G mu, and the free index will be alpha. Okay. Let us do one more thing. Let us now consider the f lambda mu. F lambda mu. So if you contract this lambda and lambda, what will be the f? What will be the f? So I need a space. I need a space. So del Lagrangian density over del beta a alpha, we have minus 1 over 16 pi. Now tell me what will happen to the f. Contract this one, that will be the f beta in the downstairs index, and contract mu and mu, that will be f beta alpha, but the indices will be in the down, so that will be f beta alpha. What happens if you do the same thing, but in the second one there is some mistake? What is that mistake? Thank you. Delta mu alpha. Mu alpha. Delta mu alpha. Okay. So if you do the second one, what you are going to obtain?
Beta alpha.
So if you do the second one, you will obtain alpha beta. Yes, alpha beta, but the index will be down again. So the second one will be f alpha beta. So can we check this? So can we check this? So let us try to do. Let us look at this. Mu and mu will let you what? Mu and mu will let you g lambda alpha. G lambda alpha, act this one, makes the f lambda, f alpha, okay? So alpha comes first, and the beta comes later. So if you continue this calculation, you will obtain f beta alpha and f alpha beta. So if you act this one, let me write this. Mu and mu, that will be g lambda alpha, and if you act this one, and that will be what? F lambda here, and the other term will come f beta. So what is this? Is it 0? F alpha beta, f minus f alpha beta, and so on, or not 0? F beta alpha, f alpha beta, and so on. Is it 0 or not? What is the property of the f alpha beta? Field strength tensor. It's an antisymmetric matrix, anti-symmetric tensor, sorry. Okay, so field strength tensor is anti-symmetric, so basically this is equal to minus f beta alpha. This is equal to minus f beta alpha. So altogether, left hand side is equal to 4 times of beta alpha, and that is equal to minus 4 over 16 pi, that will be 1 over 4 pi f beta alpha. Okay? So go over this calculation by yourself. So try to do for the other terms. Now what is the next thing we need to calculate? What is the del Lagrangian density over del A alpha? What is this? What is this term? Del Lagrangian density over del A alpha. These are the derivatives of the A's. Here only you have A alpha. If you take the derivative of the Lagrangian density with respect to the A alpha, you will obtain what? J alpha over C. So basically, we are coming to the end. So the Lagrangian density over del A alpha, if you take this Lagrangian density and take the derivative with respect to the A alpha, you will obtain 1 over C J alpha. And now we can write the equation of motion. So I am keeping the earlier Lagrange equations. So this term is del of, we have to take derivative of the f beta alpha with respect to the del beta, that is minus 1 over 4 pi f beta alpha minus for this term, and instead of del Lagrangian density over del A alpha, you will have 1 over C J alpha. Are the indices in the same places? Beta and beta free is down. So this is positive, goes to other is negative, and everything is negative. So you will obtain del beta f beta alpha is equal to 4 pi over C J alpha. Okay, do you remember this equation, presentation? What is this? This is the Maxwell's equations. So how many equations you have? What is the free index? Beta and beta is contract, alpha is free. How many? 4, 0, 1. And this is representing the which Maxwell's equations? With sources or without sources? Sources, of course. So we have the Lagrangian density, and when we applied it the earlier Lagrange equations, we obtained that the equation of motion of the electromagnetic field. Now, what happens to the other sets? What was the other sets of the Maxwell's equations? So we have, these are representing the Maxwell's equations with the sources. J0 is the charge density, J is the current density. But you have the other sets. So the question, can we find the Lagrangian density for the other set? Why we find the Lagrangian density for this, not the other one? So the answer is the following. Think about the field strength tensor. What are the elements of the field strength tensor? This is the field strength tensor. What is the elements of this? What are these? 4 potentials. The elements of the 4 potentials are the scalar potential and vector potential. How we obtain this? From these two. So we obtain the B from here is a curl of E, and the electric field, if you plug here B as a curl of E, you will find that the electric field is a 1 over C del E over del T over gradient of the scalar, gradient of the scalar potential. So these are the definitions of the 4 potentials, and coming from this set, therefore there is no need to force ourselves or study to derive the set up the Lagrangian density for the other sets. These are the definitions. Definitions of what? Definitions of the potentials. Definitions of the fields in terms of the potentials. We construct the field strength tensor using this scalar and the vector potentials. Therefore, we have only one Lagrangian density for the electromagnetic field, and that gives this equation of motion. Okay, this is the equation of motion of the electromagnetic field. How many equations? 4. 4 independent equations we have. Now, I will stop here, but before I am going to stop, you may ask me what is next. The next thing is we work with the Lagrangian density. The next step will be the Hamiltonian density. So we will put or define the Hamiltonian density as a tensor form. You will see next time, and that will give us that the covariant forms of the conservation laws. What are these? Conservation of what? Momentum of energy, energy density, momentum density, and so on. We will see this next time. And so far we find that the Lagrangian for the charged particle, relativistic charged particle, and we find that define that the Lagrangian density for the electromagnetic field. And these are the covariant equations. And the next things will be the work on with the Hamiltonian, and we will set up the canonical stress tensor and then symmetric stress tensor that will give us the covariant forms of the conservation of momentum of the energy density. We see this as a form in the chapter 6. Now we will see in the covariant forms.